Welcome to Shoreline Community College and a Global Affairs Center presentation. My name is Terry Taylor. I'm the Assistant Dean of the Social Sciences Division and the Honors College. And it is my pleasure to introduce my colleague, Charles Chip Dodd, who teaches Geography and International Studies. Chip just got back from a sabbatical where he was able to travel all around Australia and take beautiful pictures of the landscape, meet a lot of interesting people while he was there. He's been a professor at Shoreline Community College since 1998. He specializes in geopolitics. In the late 1980s, Chip was an intern at the Bureau of Intelligence and Research in the Department of State, and he could tell you about that, but then he'd have to kill you. He specialized in water, energy, resource issues, and the former Soviet Union, which was a lot of information that went away, I guess, for a brief time. He has his undergraduate degree in political economy from the University of California at Berkeley and a Master of Science degree in geography from the University of Washington. In the immortal words of Men at Work, from their classic hit of 1981, I come from a land down under, where women glow and men plunder. Can't you hear the thunder? You better run, you better take cover. Now please join me in welcoming Professor Chip Dodd.
Thank you, Terry. Thanks for attending today. And I want to say before we get started that I'm going to try and show you a little bit of my trip, but also speak to some of the earth science people in the room. So I know there's some earth science courses in here, and students and faculty, so it's going to be a little bit of show and tell and a little bit of an interesting look at Australian geomorphology and past geologic history. Maybe a better, and I'm still orienting myself to this clicker thing. There you go. Maybe it should be down, under, and to the left, because although I went to Australia in October, November of last year during my sabbatical, I actually spent most of my time in Western Australia. And there's reasons for that I'll soon make apparent to you all. Apparently it's the right clicker. Okay. So Western Australia, which by the way, I got to get this out in the open, it's WA. No one in Australia says Western Australia. Even in the media, when they report the news, for example, the weather, there's a storm system passing through Perth right now, they would report it as WA. WA has a storm through. Now, this is really confusing because when I filled out paperwork in Australia, a lot of times I had to indicate which state from the United States I was from, and they would see that WA, and it would get kind of confusing. Okay, a couple things. These numbers may not mean anything to you, but for comparison, this is the surface area of the United States. WA is 4 times the area of the state of California. So that's about a quarter of the United States, right, in terms of area. And yet the population is just about 2.5 million. So it's a little bigger than King County. So we're talking about a very, very, very low population density. And in fact, about half of that population lives within 40 miles of the capital of Perth. So Perth is the capital of WA, or Western Australia. And I actually tried to travel about as far as I could within that state, within reason. Why did I go to Western Australia? Why did I go to WA? So I'm going to discuss that. Then I'm going to talk a little bit about where I went, just for a little bit of time. And then I want to talk about the evidence for a very different Earth that Western Australia provides to us today. That's one reason I went, because I was very interested in the story it had to tell about the early Earth. And then another thing that was very interesting that really kind of overwhelmed me was the degree to which the economy in Western Australia right now is going through, and it has been going through for the last 20 years, an extended economic boom as a result of the extractive industry. If we had more time, I'd like to talk a lot about the social tensions and environmental conflicts around that, but we have limited time today. The one key thing that ties all this presentation together are banded iron formations. So if you're looking for a main theme, this is where I'm going. Hopefully this will all tie in. I'm going to talk about the banded iron formations. So, but it won't be apparent early in our presentation. So why did I go to Western Australia? First of all, it has some of the oldest continental crust on our planet. And because it's been kind of free of plate tectonics, it's out in the middle of a plate, so it hasn't been subjected to subduction and convergent collision and all that. It has a relatively unaltered surface. Also, it's been arid for some time, so much of WA has. So there's just been not as much erosion and weathering as you'd expect in other parts of the world. Also, WA, because of its size, has a lot of variability in climate and the plant and animal communities that inhabit Western Australia. So I was really interested in that. It also has a great park system. I want to comment on that to some degree. I understand we got a national park class in here, so U.S. National Park Geology course. It has some exotic landscapes, so I'm kind of an amateur photographer, and I particularly like taking photos of exotic places. So that's another thing that attracted me to WA. And then I was also interested in this extractive industry, which today I'm going to talk about iron ore, but there is also a boom occurring with natural gas and tantalum and lithium and all sorts of other things. Some of that is, although it's providing a lot of jobs and wealth for WA, it's also creating a lot of problems for people in that part of the world as well. I was also inspired by this series. So if you find this talk today interesting, this was on Nova several years ago. When I saw this 2 years ago, it clinched it for me. I'm going to go to Australia. And this is Australia, the first 4 billion years. You'll notice that there's a slight difference in the titles there. If you do a search, you'll find it under both. So I think it was released in Australia as a different title than in the US, but it's a great video series. I recommend that. So WA, interestingly enough, has some of the oldest, in fact, the oldest minerals that have been kind of accepted as by the scientific community is dated to at least, this is complicated to use, at least a 4.2 billion. So a couple times I'll have numbers up here relating to age, and the little b refers to billion. The number in parentheses is by those who dated this, that's their asserted date. This is the more widely accepted date by the scientific community. So that is very old. I don't know how many geology students are in the room or science students. That is about 100 million years after the formation of the Earth. So now, I wish I could talk about zircon crystals in more detail, and maybe we will at the end. But that is the oldest mineral that we know of, and that was found in WA about 3 years ago. Also, one of the oldest cratons. Now, we'll talk about what a craton is in a few minutes. Also, the Pilbara craton is also in WA. And then we also have elsewhere in Australia some of the earliest evidence for life. This keeps being pushed back, but hopefully you can see that date is about 3.5 billion years ago. Yeah, so what is a craton? It's the old and stable part of the continental lithosphere. So these are old cores of continents. This is granitic rock, at least initially, that's much lower density than the material that makes up the ocean crust or oceanic crust. And the Pilbara craton is one of three. By the way, it should be pronounced Pilbara, although I'll go to the American pronunciation inadvertently, I'm sure in this presentation, is Pilbara. Americans tend to say Pilbara, it's Pilbara. There are two that make up Western Australia, and the Pilbara craton is one of three from this time period. So it's the other two are in the Baltic and in South Africa, and they all date from about 3.6. Some materials in those cratons are older, but they're established as a unit of granitic rock at this age. And I wish I could say more about that. Australia, WA, which is here, hopefully you can see here, it ranges from dry summer subtropical, what some people know as Mediterranean climates, all the way up to tropical, wet, dry in the far north. And so that's a nice range of climates, including desert in between. So I was really interested in seeing that firsthand. I was also interested in the national park system. This state has over 90 national parks. And right before I went, by the way, they changed the designation of the park system. One thing I have to say about the national park system in Australia is not centralized like here in the United States, or another country I traveled to and we spent a lot of time in the national parks is Namibia. In both cases, those are kind of controlled and administered by the central government. In Australia, it's probably more similar to the park system in the United States before 1916, before it all became under the control of the Department of Interior. So there's a lot of multi-jurisdictional administration of these parks. WA administers the national parks in Western Australia, but some of them have shared control over different Aboriginal organizations. And I'm going to talk about that in more detail with Karenjini National Park, which is one of the parks I go to. So as I traveled around, this is the length of stay at different locations. Many of these were in national parks. Sometimes they were in small towns and in Perth. I don't want to belabor this except to show that I traveled a fairly decent amount. In fact, traveling in rent-a-cars, I accumulated 10,000 kilometers of driving. So that's about 6,000 miles of driving, and I was pretty tired by the end of the whole thing. I apologize for the lighting conditions in here. Some of these pictures may be compromised. Just very briefly, what I want to do is just kind of give you a sense of what it was like starting out on my way up to, we're going to go up to the banded iron formations in Karenjini National Park. That's our destination in this trip. I'm not going to cover all my travels in Australia today, but this is downtown Perth the morning after I arrived. This is very early morning, and Perth is a city completely under construction or nearly under construction. It is a boom town. The locals would say it's in a slight depression right now. I didn't see really evidence of that. It just seemed like construction everywhere. So it's got a CBD. It feels very much like that's a central business district for those of you who have never heard that term. A lot of major corporations down there, a lot of foreign capital flowing in, largely due to the extractive industries. And there I'm heading out for points north. So I'm headed out to Perth, and our ultimate destination, at least in today's talk, is going to be the center of the Pilbara region up here by Newman, between Newman and Tom Price, Karenjini State National Park. So traveled up the coast, saw all sorts of cool places. Le Sueur National Park, Nambung National Park. This is a pinnacle desert. Great silhouette of the pinnacles. These are limestone formations in kind of a sandy desert setting. Wish I could discuss this place more, but this isn't where we're going today. But I traveled through there on my way to the banded iron formations of Karenjini National Park. One thing I did not anticipate when I planned this trip, and even when I talked to locals when I provisioned in Perth, I didn't appreciate the extent of flies. I don't know if you can see, this is my camera bag. This is the first morning I'm in the bush. I'm in Nambung National Park. I was just astonished. So these are flies at dawn. They're attracted to dark things. They're after moisture. So they'll land on your eyes, your mouth, your ears, your nose, your camera, which is dark, and your camera bag. Can you guys see the flies? Okay. Yeah, they're lighter. I mean, I wouldn't say they were white, but yeah, they're all over the bag. Okay, enough of the flies. No banded iron formations yet, but here we've got my first roux is in Nambung. Pretty soon they became quite ubiquitous and a traffic hazard, actually. I was pretty happy after I saw them. Kalbarri was another national park I went to for the earth science people in the room. Fascinating place. It's most of the surface of this national park, which is up on the coast of Western Australia, well north of Perth, is Silurian sandstone. And what's interesting about this park is it preserves the oldest evidence for terrestrial life on dry land. Trackways by marine organisms that appear to have traveled at least on beach sand, maybe to reproduce or lay eggs, like horseshoe crabs do today, and other type of organisms. Sea turtles, for example, that just either mate or go up on sand to lay eggs and then go back in the ocean where it's relatively dangerous. During the Silurian, so this is about 300 or 430 million years ago, there was no terrestrial life at all. Life was in the oceans, right? And again, we're not seeing any banded iron formations, but the sandstone was gorgeous. This is a very iconic landscape image. This is Nature's Window, which is in Kalbarri. At the time, I was kind of underwhelmed. I've gotten fond of this location, though, but you'll see it if you see the Australia the first 4 billion years. There'll be some cool scenes from this formation. Not far from Nature's Window are these Eurypterid tracks. So these are tracks from sea scorpions that traveled out on the beaches during the Silurian at this site. Alluvial sand. And so not necessarily, no, I'm sorry, that was another, we're going to see the alluvial sand in a second. This is common beach sand. Can you see the tracks? Yeah, so right here. I got a better shot and a little better light here. So these guys are, these trackways are about 3 inches wide. Right, so they're not horribly large Eurypterids. These are extinct now. They got up to 9 feet long. It would have been a bad scene if you encountered them firsthand. Beautiful coastal beaches. I had to throw this in. This is in Kalbarri too. But right close to where I took that photo, like 200-300 meters from where I took that photo of the wave there, these are trace burrows. Same time period, the Silurian, in alluvial sands. So these are burrows of critters. And, whoops, this is sensitive. And it was very, very, very attractive, very beautiful setting there. This was the Mushroom Rock Trail. So if you ever get out to Kalbarri, go on this trail. Later on, second trip that I did out to Nature's Window, I ran into this. Does anybody know what this is? So, porcupine. No, this is an echidna. It's a short-beaked echidna, which is one of 2 monotreme species in the world. So this is an egg-laying mammal. And I had absolutely no expectation of running into these. They're found all over Australia, yet they're not that frequently encountered. So they're a cosmopolitan species on that continent, but I almost ran over this guy. So he's out on the road to nature's window, and he got away safe. He's about the size of a hedgehog, if you guys are familiar with it, shoebox size. Yes, it is. So the other species, absolutely, Harris. The other species is a platypus that's a monotreme. It's better known, yeah. And okay, so we got to get up to the banded iron formations. On my way up there, I just had to take this picture. Welcome to the Northwest. So this is the Northwest part of WA, right? Not the Pacific Northwest. Okay. 26 parallel, so I'm getting down towards the tropics. And in fact, by the time I get to Karanjini, I'll be at 20 degrees south latitude. So on my way there, visited Shark Bay. I'm going to get back to this site. Very important. This is a World Heritage Site where there are stromatolite communities. We'll get back to this later, but these are geologic structures produced by communities of cyanobacteria. These are very rare on Earth today, and in fact, Australia, as far as I know, has the majority of these communities that we find. They're very interesting. I'll talk about them in more detail in a few minutes. They're an important part of the story. This World Heritage Site had some great kind of interpretive information on stromatolites. The term stromatolite, by the way, refers to the geologic structure, usually comprised of sand grains that build up as a result of being captured by cyanobacteria filaments. So cyanobacteria are bacteria that can photosynthesize. And photosynthesizing bacteria want a stable place. What does photosynthesis mean? Making light or making food from light, right? So this is bacteria. They're not plants, but they do the same trick that plants do. They can make their own food using light, and then carbon dioxide and water is also an important component for the sugars they produce. I'm going to discuss them in more detail in a few minutes. I also at Shark Bay, I saw these things. I had to put one in, image of one. That is, if you can, if it's hard to recognize. That's a dolphin, which, by the way, why would I talk about this today? A dolphin. Yeah, sure. Yeah, okay. So it's a shout out to Shoreline Community College. Another thing I encountered on my way north are these things. These are road trains. These are semis that usually extend 5 trailers back. Almost always they're carrying iron ore. Maybe sometimes you'd find produce. This is the Great Northern Highway, which was actually kind of not a particularly wide road. And these things were a little unnerving to encounter. And that gives you an idea how long they are. I don't know if you can see, that's 4 trailers long. Another thing I encountered on the way north to the banded iron formations were bushfires. I wasn't actually in one, but very close to a few very large ones. They're a seasonal occurrence. They shut down the Great Northern Highway for a day. Fortunately, I wasn't quite in the vicinity when that happened. But I came through a day after the fire. The locals were very appreciative that this had happened because it had removed a lot of fuel that would have, if it kept accumulating year after year, become more of a fire hazard. Camping in Karanjini, so I'm about there. And this is where we want to go today. This is Karanjini National Park. And these are the banded iron formations, which I'm about to discuss. Gorgeous place. Although it's very remote, it was way up north. This is considered the crown jewel of the national park system in WA. It's heavily visited, and it's absolutely gorgeous. You have a series of gorges that cut through this banded iron. some nice camping facilities, which we'll maybe talk about at the end of the lecture. Did I skip over something? Yeah, it was my first astrophotography of the Milky Way, and it's not turning up here, but I did want to mention that I told people I'd throw in a couple interesting photos, not just a banded iron. So this is the Milky Way. It's southern sky, though, so I always get confused about what to press here. So if you see here, these are the Magellanic Clouds, which are only visible in the southern hemisphere. So these are nearby small galaxies that you can see. And then the Milky Way is, of course, our galaxy here. It's the Coalsack Nebula right there. The glow on the horizon, it's not pre-dawn. This is from bushfires that are about 40 miles away. So there was still that risk. It never got into the park. But it got very close to the town of Tom Price, which I'm going to discuss in a few minutes.
Was it smoky?
It was not terribly smoky. That morning, after the sun rose, you could see smoke. That was the only time I saw smoke on. So let's get back to a craton. I mentioned that these are what today to us seem like the cores of continents. Most continents have multiple cratons towards their center, and then other material kind of over the process of plate tectonics would accrete to and merge with these cratons. There are two. The Pilbara craton, which we've gone to right now on our trip here, is pretty old. That's about as old as we've been able to date a craton on the planet. Yilgarn is another slightly younger craton. Together, sometimes they're characterized as the West Australian craton, but they are separate. One thing that's interesting is the Pilbara craton is now believed to have been part of another craton, which is in South Africa, which is Cape Val craton. It was rifted apart through divergent plate action. So those of you taking geology are hopefully familiar with that process. These cratons are interesting because they're old, and in the case of Australia, they've been in a fairly mellow plate tectonic setting, at least for the last couple of 100 million years. They're relatively unaltered. In the formation of a craton, a lot of times what you get is this, so you've got this low density granite that forms, and by the way, the continents are made up of granitic low density material. They can be metamorphosed, and they can certainly have accumulations of sedimentary rocks. So there's three types of rock, right? What are they? Oh, excellent. Metamorphic sedimentary igneous. So you would expect the igneous rock, right, which is granite. That's igneous is a material that solidifies out from a molten state. You'd expect most of these cratons would be made of this because, remember, it's granite. This is low density material that as you have partial melting of pyridite and then basalt, eventually you get kind of silica. The silica melts, come out, separate out, and they form kind of this low density scum, which ends up becoming the origins of our continents. What's interesting about that process, though, is all that melting also separates out relatively rare elements that don't readily combine to form minerals, like lithium or gold or silver and tantalum. Now, some of these are really, really exotic, but these cratons can be treasure troves for kind of exotic materials like that or metals like that. And that's certainly a case in both of these cratons. Lots of gold, lots of lithium, lots of tantalum, lots of other things. And in the case of the Pilbara craton, a lot of iron ore or iron oxide minerals. And if you look at this map, actually I've got a better map. Oh yeah, so this is geologic time scale, which attempts to use a 12-hour clock to kind of indicate the age of the Earth. So you want to read this as a clock. The Pilbara craton formed about, so we're reading time like this, right? And multicellular life really arises like kind of late in the game. I love these kind of clock metaphors for the passage of time. It's better than like a column, seems to me. But so these cratons preserve part of the Earth's crust from really well back towards the beginning. And another one, we'll just pass that up. So I know this is a busy map. A lot of geology maps like this, they have to characterize so many different types of material that you got kind of a confusing color scheme here. But what I want to indicate here is that you've got over our Pilbara craton here, you've got a lot of sedimentary rock. There were times when this craton appears to have been largely underwater, under a very shallow sea. Now that's not surprising because throughout most of Earth history, from what we can tell, glacial ice that's accumulated on large land masses like Greenland and Antarctica today were rare. So for example, during the Mesozoic, we don't have evidence of any kind of glacial ice. We also believe at this time we didn't have glacial ice, and there's a lot of indirect evidence for that elsewhere that I don't have time to go into. So even a continent could be under a shallow sea, and that's kind of important. So there are marine sediments that have accumulated here, and they're a very unique type of marine sediment. And where that red circle is that just popped up, that is where Karenjini National Park is within the context of this geologic map. So that larger map that we just saw, now we're focusing in our national park where I am visiting is Karenjini here. And we're going to come back to this map a little bit later, but these are all major iron mines that have popped up, and I'm going to comment on that some more. This is in the middle of that sedimentary area that we just saw on the previous map. Karenjini National Park, by the way, like most of the national parks in WA, is relatively recent. So it was formed in 1962. It was originally called the Hammersley Range National Park. It was renamed in the 90s. It's got a very interesting, like many parks, they're called national parks. Again, most of them, or many of them, are managed by local governments, like the state of WA in this case, right? But they also have interesting multi-jurisdictional relationships with Aboriginal institutions. And in this case, there's a jointly owned Karenjini Aboriginal Corporation. When I mean jointly owned, there's two different Aboriginal groups that manage this, and they have a major role to play both in the management of the park as well as the interpretation of the park. I have to say that of all the national parks I visited in Australia, this one had the best interpretive information. Many parks have no information for the general public, or very rudimentary information. Maybe one sign at the entrance of the park, and that's it. And I wish I could discuss that more. So we want to get forward to the banded iron formation. So I stayed in several different places. What makes Karenjini really interesting is that there are 8 major gorges. These are all tributaries of the Fortescue River that have incised or cut through the sedimentary rock that I keep kind of hinting at that covers this part of Western Australia. And they're absolutely gorgeous locations. And I visited these 5. I planned to visit 7, and I had a little mishap that I'm not going to talk about. So the material that makes up the surface of this national park are banded iron, or what's called a banded iron formation. And these are sedimentary rock that is accumulated in a series of layers made up of iron oxide, magnetite, and hematite. You can see that these are combinations of iron and oxygen. So essentially, these are known as BIFs. And essentially what we have here are a mineral in which oxygen combined with iron to form a precipitate that fell out or precipitated out of the ocean. The original iron was in solution in ocean water. It encountered oxygen. It bound with oxygen. This is a ferrous oxide. You guys hopefully are familiar with rust. That's what happens with iron when it combines with oxygen. It forms a rust. But this happened in the ocean. And it happened actually on a massive scale. What's interesting about Carnegie and about the banded iron formations of the Pilbara, this is the thickest banded iron formation that we know of on Earth. There are several others. In fact, if you're familiar with the area around Lake Superior in Michigan, which is a major center of iron ore production in North America, that's banded iron as well. But it's been exploited by modern industrial economies for some time. This one was just discovered in the 60s. I'll talk about that in more detail in just a few minutes. BIFs account for over 70% of global iron ore reserves. So they're economically extremely important. This is where we get most of our high quality iron ore that then goes into the production. What do we use iron ore for?
Steel.
What's that?
Making steel.
Making steel, yeah. So, so it's extremely useful and important. The other thing about banded iron formations, though, is that they really signal an interesting development in the chemistry of the Earth. This iron that was in solution in the oceans suggests that prior to this precipitation of iron oxide on the ocean floor, there was no oxygen in the oceans. And this gives us, this is one of a whole series of clues that back in I haven't mentioned what time period this is from. So geologists have been able to date the formation of the Pilbara BIFs at about 2.5 billion years. In fact, this whole huge sequence is less than from top to bottom is less than 100 million years old. So, so it formed over a very significant, it's several hundred feet thick. And that's, it's quite a significant amount of iron oxide. What this suggests is before this time, we didn't have oxygen in the oceans, and therefore no oxygen in the atmosphere. And there's other evidence for this that we don't have time really to discuss. Now, where did the oxygen come from? We'll get to that in a second. But I just wanted to get through some of these gorges. So this is Dale's Gorge in Carnegie. These are several hundred feet deep. Usually the layers are very finely defined. There's some silicate minerals. Chert, for example, it's between each layer. And this is kind of a close-up. It's too bad you can't see it in the light here. But that's a little cricket, which I didn't notice at first. He's going to book on over in the center of the picture there. So these are each of these layers, and there's something of a debate about whether the layers are seasonal or if the layering is driven more by iron supply rather than oxygen production and it's going to end up being our stromatolites. There's going to be a connection with the cyanobacteria that we saw in Shark Bay in just a little bit. So this is out in Dale's Gorge. Again, the light is compromising this a little bit, but you might look, if you look carefully, you'll notice that there's ripple patterns on the top of this. So the top of each of these layers was seafloor, then buried by another layer. And you can see ripple patterns occasionally in these layers as they're exposed. This is a beautiful spot by Fortescue Falls. Can you see the bands? Now, what color is this?
Rust.
Yeah, rusty, kind of reddish color. So this is typical of some kind of ferrous oxide mineral, like rust. Fortescue Falls, okay. So one morning I was down in Dales Gorge, ran into these. I wish I could show you more. This is like a companion from throughout the trip. This is a white-necked heron. And he started up at the lower sequence of this formation and was just jumping up. I think he was trying to come up and surprise a lizard or some kind of reptile. He would just jump up to the next layer, and he hunted all the way up the gorge. It was kind of fun to watch. Gorgeous bird. So hopefully you can see the fine layering here. Banded iron, maybe a little too much. I should share with you all that the temperature is, during the daytime when I took these, topping out at about 102 to 104, and at night it was cooling off in the low 80s. So we're in the tropics, and we're away from the coast, so it was somewhat hot. This is Joffrey Gorge, which was quite gorgeous and extremely noisy. There were cockatoos that you rarely could see, but they were just cacophonous, constantly calling out, and I don't know if they were annoyed at my presence or not. This is Hammersley Gorge, which is visited a lot by photographers if they can make it out there, and it was absolutely gorgeous. Much more... there's iron oxide here, but you got many more kind of silica-rich deposits as well. So these are sediments that are not iron oxide, and you can see some of those here. You're lacking the red. Hammersley Gorge. Which is in the park, but it's discontinuous, so it's surrounded by Rio Tinto land. I'm going to talk about Rio Tinto in a second. That's one of the big multinationals that is extracting this iron ore. This park is surrounded by open pit mines, and in fact, there's a really large open pit mine in the middle of the park. So some of these are, I wish I could comment on more some of the settings here. So there's Dales Gorge, Joffrey Gorge, Hammersley Gorge were the ones that I spent a lot of time in. So where did the BIFs come from? They came from waste products from cyanobacteria. Cyanobacteria are bacteria that photosynthesize. And we have them today. If you don't wash out your sink, on the scale of a couple of days, you might start seeing a really thin little film of green or kind of brownish green, and that's probably cyanobacteria film that's developing there. This is a fossil cyanobacteria from WA, actually. And one of the interesting things is that they tend to create these structures called stromatolites. Stromatolites were first kind of recognized in the geologic record at the beginning of the 20th century. They weren't recognized in the field until the 1960s, I believe, early 60s, in, of all places, where do you think? Where? Where were the first kind of living stromatolites found? I say living because they were produced by living communities. They found them in the fossil record, and then we recognized the first ones in WA, of all places, in Western Australia, in Shark Bay. And they've been found in about 20 other locations in Australia, most of those in Western Australia. What cyanobacteria do is they're desperately in need of stability. They want a stable level of sunlight. That's like a major input to life for them. And they photosynthesize. They use carbon dioxide, water, and light to produce glucose, right? Sugars, food, just like plants. But they produce a waste product, which is oxygen, or O2. We have fossil stromatolites actually just outside Karenjini National Park from this time period of 2.5 billion years ago, and from elsewhere in Australia. We're not saying that there's a direct correlation between those stromatolites and this, but we do have fossil evidence of stromatolites like this. We also have actual communities living today of these. Shark Bay is a really good example. I think I just said that. So what you see are, these are growth layers starting here. What the bacteria do is they produce filaments that trap sediment, and that keeps them kind of firmly anchored at a location. And then they grow kind of upwards through the sediment, and they produce another layer of anchored sediments that then harden and become a rock eventually. The term stromatolite refers actually to this rock structure. It's biologically constructed. There is not one species of cyanobacteria. There's a whole community, actually they're layered, and they are adapted to different levels of both light and the gas environment changes within these layers. So the idea is photosynthesis. Now today, this isn't Shark Bay, it's nearby. This is actually a lake that I went to by the town of Cervantes. You don't encounter large communities of cyanobacteria today because they have lots of predators. So a good example are mollusks like snail and slugs. They would eat and graze on a cyanobacteria film. But in some of these places like Shark Bay and Lake Thetis here outside of Cervantes, the salinity levels are much higher than in the ocean. There's really high rates of evaporation. The inflow of fresh water is really low, or even marine water. And so the salinity levels are about 3 or 4 times what they are in the open ocean. And that's just too hostile for grazers of cyanobacteria. So there's very few environments that support these today because all of these other organisms evolved. But we believe during the Archean, which is a long time period that these banded iron formations and these ancient stromatolite deposits date from, cyanobacteria didn't have anything to worry about in terms of grazing organisms like snails or slugs. So we think they were extremely commonplace. They exist in very extensive areas, and there's indirect evidence that that's the case because of the enormous amount of oxidation that occurred to the iron that was in solution in the ancient oceans that created these BIFs. And by the way, I think I mentioned this, but these BIFs have formed in many other continents. But this sequence here in the Pilbara is the thickest that we know of. This is Shark Bay. You're seeing, I never encountered really good tidal conditions, but what you have here are mounds. There's cyanobacteria out here, and they've stabilized the sand. It's actually hardened somewhat. These filaments that are kind of a mucousy thing that traps the sediment, it actually solidifies into what feels like a hard rock. Interpretive sign, just emphasizing that there's a big community of different types of bacteria here. And I'm going to move on and talk about, this is a reconstruction of what we think the Archean coastline maybe in WA looked like 2.5 billion years ago. Today that coastline, at least at Port Hedland, is dominated by these things. These are iron ore ships headed north or headed probably to India or China. Those are the two major consuming markets for the iron ore that's mined from these banded iron formations. There's a whole constellation of open pit mines in the Pilbara. Some of these are brand new. The oldest is the Tom Price mine, which I visited, that opened up operations in 1966. Tom Price is maybe an odd name for a town. So Tom Price and Newman are the two regional centers in this part of the Pilbara. Karenjini National Park is here. I don't know if you in the back can see this. This is the Marana du Main, which is in the middle of Karenjini Park, and that's been operational since 1994. I don't understand the history of why that was held on to within the boundaries of the park. Now, the park did grow from its creation in 1962 somewhat. I do want to mention something about the name of Tom Price here. This is named after the vice president of Kaiser Steel, an American by the name of Tom Price, not related to the Trump administrator who lost his job last year. Was he Department of Transportation head, right? Not the same guy. So Tom Price was not a trained geologist, but he was one of these jack of all trades kind of corporate executives. He knew a lot about different aspects of science and economics and social sciences, etc. And he, as head of a multinational corporation, which Kaiser Steel was, placed a lot of resources on a hunch that the Pilbara would have iron ore deposits. These banded iron formations had not been discovered in the 50s, and they prospected quite extensively for them, which, by the way, doesn't mean drilling into the ground. It just means getting people out into the countryside. And this is before we have satellite imagery, just before that. And in 1965, they had struck iron ore. In this town, Tom Price was this was the first mine in the first town built in what would be a mining boom. I was just amazed going out there, seeing all these mines, seeing all the miners in places like Port Hedland, even Perth. Some miners actually commute from Perth, which is over 1,000 miles away. They fly out here and work, usually in 12-day shifts. That this whole mine boom has been going on over a time period that's shorter than my existence on the planet. So I'm actually older than this iron ore boom that's been going out in the Pilbara, which that probably doesn't surprise you guys, but it surprises me. Yeah, if you look at the data on these things, a lot of them are very recent. I want to move forward and this is a map of Australia's iron ore reserves, and you can see that although there's smatterings of them elsewhere, they're heavily concentrated in the Pilbara, and this mining boom. So this is, it's absolutely unfathomable how rapidly this has buoyed up the Australian economy and WA's economy. I don't know if you can see, this is Australian metal ore and mineral exports in millions of Australian dollars since 1969. And this is largely based on iron ore exports, although there's a lot of other metals. I'm almost done. I'll leave you with this. Iron ore now, Australia's contribution to the world iron ore economy is absolutely amazing. So almost 40% of all the iron ore production in the world comes out of Australia, and most of that from WA. It's an absolute amazing concentration of a strategic resource that 40 years ago was really not on the radar, so to speak. So that's fairly amazing. Australia also, for reasons that we're running out of time but are related to some of the processes with these cratons, are major sources of all sorts of other, the top four here are all dominated by production in WA. Lithium, I'll just leave you with this. This seems to be the next really big boom mineral for WA. And what is lithium used for? Batteries, yeah. So, and actually when I was in Australia, Elon Musk visited several times, and that was a big deal in WA. Okay, so thanks for your time. Thank you.